So we need a program to actually compile with this thing. So if I just create a simple function, oops, can't type. I'll return 0 and I will put hello world. Okay, so that's my basic program. So I can now compile this using MIPS, Linux, GNU, GCC in exactly the way that I would compile normally. Compile it, and I can see that what's come out is this thing called a.out, which is the default name that comes out of GCC. If I use this quite useful command called file, I can actually ask, well, what is a.out? And I can see it's a 32-bit executable. It's designed for MIPS32 and it's dynamically linked. So I have my executable. Now I need something to run it. So the thing that I'm going to use to run it is this emulator called QEMU. QEMU is both a virtual machine in the sense that VirtualBox or VMware is, but it also has this nice ability to actually emulate processors at reasonably fast speeds. And not just a small emulation, it emulates the whole thing. So you can run entire operating systems or arbitrarily complex programs. So again, I go looking in my package list for QEMU. And there's various things here. So QEMU is the main processor agent. These are all things that allow you to actually run a complete operating system under QEMU. These are things that allow you to run a binary. So really we only need QEMU user. So again, using apt-get, sudo apt-get install QEMU user. Another download. And I should now have QEMU. I've actually got multiple different processors here now. So even though this is an x86 machine, I now have the ability to run executables from any of these platforms. Some of these you might recognize, like for example x86-64 or MIPS. Some you might not know so well. So for example, Microblaze is a soft processor that Xilinx use in their FPGAs. What else do we have? PowerPC is used in slightly older things like the PlayStation 2, all those kinds of things. So if we now take QEMU MIPS, because that's what our thing is, give it the executable, run it, we get this problem that it's trying to load a .so file, which is a shared object. And while we could fix that problem, it's actually more hassle than it's worth. So remember that when we looked at a.out, it did say it's dynamically linked, and it actually says it's linked against this dynamic library here. So to fix that, we will simply say everything must be statically linked. So any functions that test.c uses should be embedded in the executable itself. So anything from the C standard library, for example. So double checking what this is now, it's still a 32-bit MIPS executable, but now it's statically linked. So I will try again to do QEMU, and it prints hello world. Awesome. So we can compile MIPS programs, we can execute MIPS programs. So that's our tool chain set up for creating programs and seeing if they work. So now let's look at the assembly side of things. So if we ask GCC not to link it, but to actually assemble it, so minus capital S is for assembly, and let's say that the output should be test.s, then what I've now got is test.s. So if I look at that, I end up with this assembly file which contains lots of things that you recognize and lots of things you might not. So there's all of this declaration stuff at the top, which has sort of metadata about what file it came from, things about which ABI it is, various things about floating point. It has labels that you probably recognize as saying this label refers to the thing that follows it. So in this case, it is a label talking about the constant string hello world, because hello world is going to have to be embedded in this executable somewhere. This whole thing is actually in the .rdata section. So rdata stands for read-only data, and that makes sense because string literals in C are read-only. You're not supposed to modify them. Following that is the text section, and that actually contains the executable code for the program. So it's .txt, which I think is for type ext. I don't know. It's always been .text. Maybe because you read it to, I don't know. And then within this we have our main function. So that's a label for the entry point of our program. And you can see various metadata here to do with things about the frame. So he's actually saying something about the frame pointer, the register that's being used. There's also some stuff about how much of the stack it's using. This is not strictly speaking necessary, but it's useful for a full compiler. Once we go into main, we can see immediately we can see some stack manipulation. So $SP represents the stack pointer in the GNU ABI. So I've mentioned the GNU ABI. It's worth actually looking at what that is. So if I search for GNU MIPS, maybe I should say ABI. That's 64-bit. Let's just search for MIPS ABI, it's probably easier. So here is a fairly typical document. And so this is a listing of all of the numbered registers that we know from MIPS. Bearing in mind that in MIPS, none of these registers are special apart from 0, so there's no meaning to these registers. So what an ABI does is say, by convention, v0 and v1 will be used to return a value from a function. By convention, a0 through a3, which is registers 4 through 7, will pass the first 4 integer function arguments. If you have more than 4 function arguments, they all need to be passed on the stack, but the first 4 can go via registers. There's some things like temporary registers, so T0 to T7 are just for use within a function. So if you're evaluating some maths and you need somewhere to stash a value, T0 to T7 are available for you. S0 and to S7 are registers that you can use to store things, but those actually have some kind of permanence, because if you call another function, S0 to S7 should be preserved by that function. Either it won't use them, or if it does use them, it will put them on the stack and then restore them before they return. There's other things like more temporaries. Then a global pointer, which is used to give the base of any global data in the program, like sort of the strings. A stack pointer and a frame pointer, which comes back to the stuff from first year architecture. And the return address, which is 31, because as you've seen, jump and link actually in MIPS1 writes register 31. These could be anything. We could have done any mapping, but these were decided by somebody at some point, and everybody decided to agree with them. So coming back to our code, we can then say, well, we are decrementing the stack pointer, which means that we are reserving this much space on the stack. This is in bytes, and so that means that we are reserving 32 divided by 4 words on the actual stack. And you can see that the first thing it does is to actually save register 31, because eventually we're going to have to use 31 to get back to whoever called main. It also saves a frame pointer because it needs to store the frame. Going a little bit further down, we can actually see the call to puts. So all our function did was actually have a constant string and then print it. Here you can see the loading of the constant string, remembering that the constant string was defined at this label here. So we load up our immediate, the top 16 bits of the address, we add on the low 16 bits, and now register 4 contains a pointer to that string. Looking at our ABI, register 4 is the first argument to a function. Puts only has one argument, so that's the argument setup. We then need the address of the function that we're calling. So we load the address of the puts function. At this point we don't know what that address is, but we're going to find out what that is at link time. That's the job of the linker. For some reason it loads it into register 2 and then moves it to 25. Who knows why, but that's okay. And then it does a jump and link register to the address of puts. So jump and link is going to overwrite register 31, which is why we had to save register 31 up here. Once that thing returns, we will load back in our frame pointer, do some fiddling of the stack pointer. Then the very last thing we do is jump to register 31, because that will return to whoever called main, whatever that was, the operating system or the standard library. So that's our assembly. We can then use GCC to actually assemble this thing. We don't have to use AS, and we can say we want it to go into an executable called test. So now we actually have our original a.out and our new test, and check in. Oh, we've dynamically linked it. We should probably statically link it. So statically linked, and now we can, just like before, say QEMU test, and there we go, hello world.